Proceed with the program, and we're very happy to have Sabine Harribey, who will talk on a new approach to ON breaking interfaces and boundaries.
Thank you. So first, I would like to thank the organizers for the invitation to this very nice workshop. So the work I'm going to present today is in collaboration with Igor Klebanov and Zimo Sun, who is a postdoc with Igor. And it's still a work in progress, so please interrupt me and ask questions or, yeah. Okay, so first let me start with some motivations. So as you know, the critical ON model is of very interest, and it's one of the most thoroughly studied classes of 3D CFTs. And there are multiple reasons for that. And one of them is that we have a lot of tools to study it analytically. So we can have an epsilon expansion. We have a 1/n expansion that also allows us to study some non-perturbative effects. And you also have some numerical tools like bootstrap, for example. But then this describes very specific classes of CFT, and you might want to describe some physical systems that have impurities, for example. But then one thing to do is to introduce some defect to your CFT. So you can introduce a defect that would be maybe localized on a line or a surface. And then if your defect is actually of codimension 1, we call this an interface. And you have related problem where your codimension 1 defect, you have the codimension 1 defect, but then the extra dimension is only over half space. And in this case, it would be boundary CFTs. And in this talk, we will be interested in one particular case where your defect will break the ON symmetry to ON-1. And this kind of defects or boundaries are often called extraordinary in the literature. Okay. So there have already been a lot of studies specifically on surface defects, so defects of dimension 2. And so also more in condensed matter. And recently there were some studies where, with a mix of RG analysis and 1/n expansion, they were able to show the existence of a universality class in 3D called extraordinary log. So extraordinary because it breaks this ON symmetry, and log because they found some log in the correlation function of the CFT. And then even more recently, very recently, last month, there were some papers where they studied a d-dimensional bulk with a defect of codimension d-2, so a surface defect. And then the defect was quadratic in the field. So by this, I mean that they introduced in the action a term like this, by square schematically. Okay, so they introduced some terms like this in the action, either for a quartic ON model or a cubic ON model. And they computed, so 4 minus epsilon or 6 minus epsilon. And they were able to do that both in the case where you don't break ON symmetry and in the case where you do break ON symmetry. And they could also compare 1/n expansion with what was done directly in dimension 3 and find some singularity. But here we want to have a different approach to these surface defects. So we won't start for a defect of codimension d-2, but a defect of codimension 1. So our defect will not be necessarily a surface defect, but it will be an interface. It will always be 1 dimension lower than the main theory. And we can still do a 4 minus epsilon expansion. And in our case, the defect will not be quadratic in the field, but cubic. So let me explain why cubic. This is a bit more general. So schematically, the type of theory we want to study will have this kind of action. So you have a d+1 dimensional bulk here, and you have an interaction of order n. And then you want to introduce a defect that is of codimension 1, so only d dimension here, and of order p. And then you can wonder for which values of d, n, and p you have criticality or marginality. So to do so, you can just do some counting of dimensions. So the UV dimension of the field here, because we are in d+1, it's d-1/2. Then it means that this interaction here is marginal when you have this relation between d and p, so when this is p over p-2. And then going back to the bulk, you are in dimension d+1, so it will be 2p-2 or p-2. And then the operator that would be marginal in the bulk would be phi squared to the p-1. So you can actually study a lot of theories like this. So if you want to have the dimension of the defect to be 3, then you will have a quartic interaction in the bulk that will be marginal and cubic on the defect. But you could also take dimension 2 here, and then the bulk would be sextic interaction and 4 for the defect, and etc. You can continue if you want order 8 on the bulk, then you would be in dimension 5/3 and order 5 on the defect. So the case with n = 6 and p = 4 was studied with a boundary in this paper recently. And here we will look at the case where the dimension of the defect is 3 and we have quartic interaction in the bulk, cubic on the defect. Yes?
Just a very basic, naive question. The field depends on d+1 variables. So dimension d+1. Yeah.
Yes.
And when you, in the last term, you integrate only over d variables.
Yeah, so this is localized at, so if you call y the extra dimension, this will be localized at y = 0. Okay. Other questions on? Okay, so that's the spirit of what we want to look at. So now in this talk, I will first look at a generic multiscalar model to be able to compute generically the beta function. And then we will apply to some different symmetries. So we will look at n = 1, then to the On-1 vector model. And I will also mention briefly symplectic fermions. And then in the end, we will see the case with a boundary instead of an interface. Okay, so the model we want to study and compute beta function for is the following. So now our field is vector field with indices taking value from 1 to n, and we have this coupling constant that also has indices. So this is what is typically called multiscalar models. And so the coupling constants are fully symmetric tensors. So in general, you have a high number of couplings, but then you can specify, and we will see how we can specify to On, etc. But the subtlety here compared to usual multiscalar model or model where you don't have the second term here, where you just have this, is that we will have quite non-trivial propagators on the interface. So, and this you can see by going to momentum space. So if you want to go to momentum space, you have to Fourier transform the free propagator. But here we will Fourier transform it only along the defect direction because we have 1 dimension less. So the expression of the free propagator in direct space is the usual one. But here we integrate only over d dimension. which means that in the end you can perform this integral. And here you will obtain, instead of a power of p square, you have only p. And then you can derive the interface to bulk propagator when one of the y is 0. So this field will be an interface field and this one a bulk field. And you will have this propagator in sort of a mixed representation between momentum and direct. And then the interface propagator, where both y are 0, will have this expression. So that's what will really make this model different to usual field theory, and that will give different results, especially for the values of the Feynman integrals. Okay. Is that okay? This. Okay, so then we want to see what are the divergences in our model. So for that, we will do some power counting in D equals 3. And kind of expected that the 2-point graphs will be power divergent. And for a cubic theory, we have the 3-point graphs that will be log divergent. And here we also have a subtlety with the wave function renormalisation. Because it will come only from the bulk coupling. It will not be modified by the boundary couplings because of the form of the propagator on the interface. And so here it will be neglected. Okay, and for the scheme, so as I said in the introduction, we want to do some dimensional regularization, epsilon expansion, so D equals 3 minus epsilon. And we will do some BPHZ subtraction. Okay. So what are the graphs we have? So I'm going to do only one loop in this talk, so very perturbative. But okay, so for the 3-point function, we have 2 contributions at one loop that are actually very different. The first one is a graph that has only cubic couplings. So it's really an interface contribution. It's only on the defect. And then the second one, which will be the tricky one, is a graph that has both cubic and quartic coupling. So it's a contribution from the bulk contributing on the interface. And so we will have one coupling here, the quartic, that will be in the bulk. So we still have this y coordinate, but here it will be only an interface coupling. So, sorry. So then these 2 graphs will give us the bare expansion. So the 3-point function have just a bare coupling, the contribution only on the interface, and then here the contribution, the mixed contribution. Here we have added 2 terms to conserve the permutation symmetries in the 3 indices here. And as I said, the integral T is quite standard to compute. So we just compute it in momentum space with the interface propagator, nothing weird. But for B, because we have both quartic and cubic coupling, we have to be careful and use a mixed representation. So the interface coupling is integrated here, D dimension on the interface, so in momentum space. And here we have the extra dimension for the quartic coupling in direct space. So it's just a bit more subtle to write, but then the integral is not very complicated to compute, and we still have our epsilon expansion. Okay. So doing that, we obtain, we can compute the beta functions. So, yeah. So it's D here, D, then it's 3 minus epsilon. So you compute this integral for D equals 3 minus epsilon. For 3 minus epsilon, this integral, you can rewrite this as a 1-dimensional integral since you only have the momentums, and then you obtain an a gamma function basically, and this gamma function is like 0 for d equals 3 typically, and so you obtain like a gamma of epsilon. Okay, so then we can compute, we have everything to compute the beta functions. So I think most of you are familiar with this, but I will still go over the method to be sure. So what we do is to identify the running coupling with the dimensionless 3-point function. So that was the bare expansion I did. And then I introduced this parameter mu to make it dimensionless. And then the beta functions will be the scale derivative of the running coupling. And then it's the usual method to compute this. You derive the bare expansion here with respect to mu. You invert the bare expression to obtain the renormalized series, and then you can substitute the bare coupling by its expression in terms of the renormalized one. So doing that, we obtain the beta function for the cubic coupling. So here we just have these two terms. So this one was coming from the graph with only the cubic coupling, the interface term, and this one was the mixed term. And then, of course, we also have a beta function for the quartic coupling, but it's really in the bulk and it's not modified by our interface coupling. So it's just the usual beta function for a quartic multiscalar model. And so this is very well known. You can find this in books. Okay, so now we have these very generic beta functions, but I don't want to compute a fixed point for this model. Now I want to apply it to the symmetries I'm really interested in. And we just went to this first, because then it's very easy to apply it to different symmetries and directly have expression for finite n more easily. Okay. Before I go to the other, to the application, any question on this first part? Okay. So the first thing we can look at, the simplest, is n equal 1. So now our field is just a scalar. So we have the usual phi 4 here and phi cube here. And we only have one cubic coupling and one quartic coupling. And so the beta functions that were here, they just reduce to these expressions. And we can first look at what happens if we have a free bulk. So if we take G4 here to be 0. And what we obtain for the cubic coupling is a stable, purely imaginary fixed point. So it's very similar to the standard Yang-Lee model. So the Yang-Lee model is just this, the phi cube. So not on an interface or anything. So it's this phi cube model where they have this famous purely imaginary fixed point. So yeah, but we are more interested in looking at interacting bulk, really a defect of a main theory. And in this case, for the quartic coupling, it's just the usual Wilson-Fisher fixed point. And then for the cubic coupling, we find two non-trivial fixed points and real this time. But they have negative critical exponents, so they are unstable. But then it's maybe not so problematic because we seem to always have at least one relevant direction, because here in this case, the cubic coupling was stable, but the fixed point where G here equals 0 is actually unstable. And here we have the opposites. And only the trivial fixed point is actually stable in this case, but we can still compute some dimensions of operators and study it. Okay, but that was just a little bit of yes.
I cannot understand your last equation. It makes no sense to include 7/6 epsilon plus all the epsilon. What do you mean?
All of epsilon square, sorry, there's a typo. Yeah, I will come back later to how we compute these quadratic operators. We will look at it more for ON. Yeah, that's a square missing here. Okay, but this was more of a warm-up, and we are really more interested in the vector model, in the ON. So here, the field now is a vector, and then, so I think you're familiar with ON phi4. So here we have the phi4 with lambda 4. And then for the cubic interaction, when you want to do a cubic vector model, you have to break ON invariance. So how to make a cubic interaction with a vector? You have two possibilities. You can take two vectors and contract them, and then a third one at a specific values of the index, or you can take 3 times the same vector. So that's how you build a cubic vector model. But of course, here, if you have n vector field, this is not ON invariant, it's just ON minus 1 invariant. And so that's how here we break the ON symmetry to ON minus 1. And it's really our defect here on this interface that breaks this symmetry. And this here is really how our approach is different to what was studied before, because before they studied this surface defect that does not break ON invariance. If instead of phi square here, I do hi. This does not break the invariance, and it's just when they compute the fixed points, at the fixed point, they found some of them that breaks the invariance. Here, we really break it from the onset. Okay. And then now, because I first studied the multiscalar model, I can obtain the beta function for this very easily. I just have to set some values of my couplings before like this. So here is just to have this kind of double trace contraction, and here one coupling for the terms where 2 fields are contracted, and then another where we have 3 times the same field. Okay, so then I can just plug in this in my previous beta function, and I obtain immediately the beta functions, the one loop beta function for the ON minus 1 model. And they are quite simple, they do not look too complicated. So again, for the quartic coupling, it's the one you know, it's the usual one. And then for the cubic, we have terms here that come purely from the defect, and then some mixing term between the bulk and the interface. Okay. Okay. And again, we can first look at the case where here I take the quartic coupling to be 0, so the free bulk case. And here we find two regions. So the first one at n equal 2, we found 2 pairs of purely imaginary fixed points, one stable. And those 2 pairs, actually, one of them was corresponding to 2 decoupled copies of the n equal 1 case, where one of them was at the trivial fixed point and the other had the interacting. And the second one was 2 decoupled copies where they were both interacting fixed points. Okay. And then for n greater than 2, we always have 1 pair of real fixed points, but unstable. And then again, we have some purely imaginary fixed point where the first one is 0 and the second one is non-zero. So these correspond again to n decoupled copies of the n equal 1 case. And we also have some pairs of complex conjugate fixed points, but with complex critical exponents. So here, in this case of the free bulk, because we have these imaginary terms arising in the critical exponents, we don't have unitarity for sure. And so then it's a bit less interesting because we want to try and compare to condensed matter model where they do have this unitarity. Then we can look at the interacting bulk case. And so here we have more different regimes. So again, n equal 2 is a bit particular, where we have all real fixed points, but unstable. And then we have some appearance of complex fixed points, and above 5, we always have one that is purely imaginary and stable. And we can actually compute a critical value of n, above which we only have complex fixed points. So at low n, we have some real fixed point, and then above certain n, they are all complex. And at the stable, purely imaginary fixed point, we can also compute the quadratic operators, and they have real dimension within unitarity bounds. So it sounds a bit more promising. Okay, so this was a bit numerical analysis for low n, but we can analytically look at large n. And so here I just reparameterize my couplings like this, because I know that we have a purely imaginary fixed point at large n. And we can find this 1 over n expansion. And you see, if I take n to be exactly infinity, the first one will be 0, and I only have a non-zero contribution for the second one, so it looks, again, a bit like decoupled copies. And we can also have the large n expansion of the critical exponents that are, again, positive and real. So up to this point, we have stable fixed point with no nothing that blatantly violates unitarity. So this seems like a promising fixed point to study this extraordinary universality class. But we can go a little bit further and also look at the dimensions of quadratic operators. So here we have 2 operators, so either phi I or phi square. And we can compute their dimension, and again, they are real and within unitarity bounds. So that's quite good at large n, and they correspond to this mixing of the operators. But of course, we computed only the dimension of those operators, so we don't have a proof of unitarity. We just have that some hints up to now. Yes, but then we will, so as I said, it's still a work in progress, and we still need to compare those large n expansion with what has been done with surface defects, because for now we are not sure if we are in the same universality classes as what they call extraordinary in condensed matter with the surface defect, or if this approach actually describes another universality class. So we still need some work to answer that question. Okay. Are there any questions on this part? Okay. So then I just wanted to briefly mention symplectic fermions. So it's just a little bit of a variation on the same model, where we can take m pairs of symplectic fermions and 1 scalars. So they are anti-commuting variables here, and you have your fermions here, and then the scalar. And this is actually simple to study from what we already done, because it's just setting n to 1 minus 2m in the previous model. And here for general m, we have that this defect breaks the OSP 1-2m symmetry to SP2m. So that's also why we wanted to look at that, because it's a bit reminiscent of what happens with ON, where you have this extraordinary class that breaks ON to ON minus 1. And here we can have a similar phenomenon. The only way you could preserve it would be at m equal 1 if you have this relation between your 2 couplings. Otherwise, you would also be in the breaking case. And then we looked again, so at the beta function at 1 loop. And so the quartic coupling now has this expression, and you see that here it could be negative for some value of n, but you need the quartic coupling to stay positive. So actually, the sensible values of n to look at are below 4. So we look at this, and at m equal 1, we have pairs of real fixed point and one that actually preserves the symmetry. But again, we have this thing that only the trivial one is stable, with the other one are again relevant directions. And then between 2 and 4, it's a little bit less interesting from the point of view of if you're interested in having unitarity, because we only have complex fixed point with complex critical exponent. Okay, but still it could be a bit interesting to pursue this further to see if we have some similarity to the extraordinary class they have for the ON models. Okay, so now the last thing I wanted to look at was the case where instead of an interface, we look at a boundary. So for the boundary, it's the same. So here I will only do the ON one. So for a boundary, it's the same model as the one I wrote before, but here the extra dimension is only integrated over half space. And so naively, you could think that, oh, it's going to be exactly the same, just with a factor 1/2 at some point. But that's not true. It's a bit more subtle than that. So to have something non-trivial, we chose Newman boundary condition. And then we have 2 terms in the free bulk propagator because of this boundary condition. So the usual one, and then a term where instead of having the difference between the extra dimension, you have this sum. And so this will change our propagators in momentum space. And so we will just do the same and Fourier transform along the boundary direction. But then because we have here 2 terms and we are also integrating over half space, we won't have this factor 2 here that we had before for the interface case. So then the pure boundary graph will have a factor 2 for each propagator. But this could be absorbed with a rescaling of the cubic coupling. So up to this, it seems to be the same. But for the boundary to bulk graphs, we will have a factor 2 for each propagator, but also the extra dimension will be integrated only over half space. So this is not a simple rescaling of the coupling constant. And so it means that the boundary case are actually qualitatively different from the interface case. They are not just related by some rescaling or some global factor. So it's also sensible to study both those cases separately. Okay. And for this boundary case, in the case of free bulk, I wanted also to mention, for those that are familiar with long-range model, the link with this long-range model. So those long-range model, they are not with interface or anything, it's just the main theory in D dimension. But they have the particularity to have this non-trivial power of the Laplacian to zeta, with zeta strictly between 0 and 1. And so in those models, the propagator in momentum space is 1 over p to the 2 zeta. And when you study marginality, it will be for value of zeta and not d. And for example, for cubic interaction, it would be for zeta equals d over 6. So then those models, you can do epsilon expansion. So instead of being in d, it will be in zeta, d plus epsilon over 6. And if you look at what I had here, I had something a bit like p to the 2 zeta, but with zeta equal 1/2. And so the thing is here, if you study this long-range model, and then in your epsilon expansion at the end, you put d equals 3 minus epsilon, you will get here zeta equal 1/2. And so actually these boundary models are equivalent to long-range model with zeta equal 1/2. So when you have the free bulk, and this is kind of very important because in condensed matter and statistical physics, long-range model were very thoroughly studied. And so that's why for the boundary case, we will be mainly interested in looking at interacting bulk, because free bulk will just correspond to other theories studied before. Okay, so we did that for the interacted bulk. And so after rescaling the cubic coupling, we obtained the same beta functions with just here a factor 2 in front of the quartic coupling. But since it's not just a rescaling of the coupling, it will change qualitatively the fixed point we found. And we have only real fixed point for n equal 1. And then between 2 and 16, we have complex fixed points. And here the critical n will be at 17, where we have the appearance of some purely imaginary stable fixed point. So it's a bit similar to what happened in the interface case, but really the critical ends are different. Okay, so to conclude, we studied some interface defects with cubic interactions, and in the case of n equal 1, we found a real fixed point, but unstable. And then at large n, we were able to find one pair of purely imaginary stable fixed points, and we computed the critical n above which we only have complex fixed points, and the stable ones are always the purely imaginary one in these models. And then, as I mentioned, this is still work in progress, so we have still some questions to answer. So, especially about unitarity, because even though everything is within unitarity bounds, we still have those purely imaginary fixed points. And also about the extraordinary universality class, because even though we are also breaking ON to ON minus 1, since we are coming to this problem from a different approach, we are not sure that what we are describing is the same universality class or if it's a new universality class. And for this, we could maybe try to go to epsilon equal 1 to have a dimension 2 to really have a surface defect and compare with some condensed matter work. But here we have only the one loop results. So in order to do that, we will first need to push to higher loop. So 2 loop would be not too complicated, but then 3 loops will be quite involved for this model, because for a cubic interaction with this 1 over p instead of 1 over p squared, 3 loop has never been done before. It will be a bit more involved. And then also something that is quite interesting maybe for next project will be about monotonicity theorem. So those you have theorem in QFT that tells you that you have a quantity decreasing along the RG flow. So in D equal 2, this is the C theorem with the central charge. Then you have A theorem. And in D equal 3, you have the F theorem telling you that the free energy on the sphere must decrease. And recently, there was some work about similar theorem, but for defects CFTs, so either with some free energy or some other functions. And so it would be interesting to see if our defect CFT also respects this theorem, because because these theorem are actually theorem for the C theorem, F theorem, but they are not yet proper theorem for defect CFTs. So it would be nice to see if this respects this more conjecture. And yeah, that's everything I wanted to say. Thank you for your attention.